What if I told you that deep within the cosmos, there exist celestial objects so dense that a mere teaspoon of their matter outweighs entire mountains? What if I said that some of these objects spin hundreds of times per second, firing beams of energy into space like cosmic lighthouses? These are neutron stars, stellar remnants of unimaginable violence, and among them, pulsars stand as some of the most extreme entities in the universe. But where do they come from? And how have they shaped the very fabric of our galaxy? Deep within the constellation Taurus, some 6,500 light-years from Earth, lies one of the most breathtaking remnants of a stellar explosion, the Crab Nebula. Listed as the very first entry in the Messier catalog, this vast cloud of interstellar gas has fascinated astronomers for centuries. It was first recorded in the 18th century, but its true origins trace back much further, nearly a millennium earlier, to the year 1054, when a brilliant supernova erupted, briefly outshining the entire night sky. Over the centuries, as our understanding of the cosmos deepened, astronomers began to suspect that something extraordinary lay hidden within the heart of the nebula. By the late 1960s, with the advent of radio astronomy, their suspicions were confirmed. Nestled within the remnants of the ancient supernova was an object both small and supremely powerful, a neutron star, spinning rapidly and emitting pulses of radiation with clockwork precision. This was a pulsar, one of the most enigmatic and extreme celestial bodies ever discovered. Neutron stars do not arise from ordinary stars like our Sun. Instead, they are born from the fiery depths of massive stars, collapsing under their own immense gravity in the final moments of a supernova. The result is an object so dense that it defies human comprehension, teetering on the very edge of becoming a black hole. Yet, far from being mere relics of destruction, these pulsars play a fundamental role in enriching our galaxy with the building blocks of life. The story of a neutron star begins in the heart of a dying giant, a star that has exhausted the nuclear fuel that once sustained its brilliance. For stars like our Sun, this conclusion is a gentle transition. They shed their outer layers and settle into a stable white dwarf state, no longer fusing elements but still glowing with residual heat. However, for more massive stars, those with at least 10 times the mass of our Sun, the end is far more dramatic. These behemoths do not simply fade away, they explode in one of the most cataclysmic events in the universe, a supernova, a detonation so powerful that for a fleeting moment it can outshine an entire galaxy. As a massive star nears the final stages of its life cycle, it undergoes a series of increasingly desperate nuclear reactions, burning through heavier and heavier elements in a futile attempt to sustain itself. Hydrogen fuses into helium, helium into carbon, carbon into neon, neon into oxygen, and so forth, until the core is composed of iron. Unlike previous fusion reactions, the fusion of iron does not release energy, it consumes it. This marks a turning point in the star's fate. With no outward radiation pressure to counteract gravity, the iron core succumbs to its own immense mass. The outer layers, no longer supported by fusion, crash inward, compressing the core at velocities approaching a significant fraction of the speed of light. In an instant, the star's core, once spanning thousands of kilometers, shrinks to a diameter of mere tens of kilometers, while the infalling layers rebound off this newly formed ultra-dense object. This rebounding energy triggers a supernova explosion, blasting away the outer layers into interstellar space while the core remains behind. What happens next depends on the remaining mass of this stellar remnant. If the collapsed core retains more than approximately 3 times the mass of the Sun, gravity is too powerful for any known force to resist. The collapse continues indefinitely, crushing matter into an infinitely small singularity, a black hole, an abyss from which not even light can escape. But if the core's mass is below this critical threshold, a different fate unfolds. The collapse halts, not because of thermal pressure, as in ordinary stars, but due to a remarkable quantum mechanical effect known as neutron degeneracy pressure. This phenomenon arises because neutrons, like electrons, are fermions. They obey the Pauli exclusion principle, which states that no 2 identical fermions can occupy the same quantum state simultaneously. As the core contracts, Free electrons are squeezed so forcefully into atomic nuclei that they merge with protons, forming an abundance of neutrons. These neutrons, in turn, resist further compression through degeneracy pressure, stabilizing the core against complete gravitational collapse. The result is a neutron star, an object of almost inconceivable density. A neutron star is no ordinary stellar remnant. It compresses up to 2 solar masses into a sphere only 20 to 25 kilometers wide, roughly the size of a metropolitan city like Boston, Frankfurt, or Cincinnati. The density of such an object is staggering. A single teaspoon of neutron star material would weigh over 1 billion tons on Earth. This is because neutron stars are composed almost entirely of nuclear matter, a state of matter even denser than atomic nuclei. With such extreme compression comes an equally extreme gravitational field. The escape velocity from a neutron star's surface exceeds half the speed of light, meaning anything that ventures too close would need to travel at relativistic speeds to break free. The curvature of spacetime around such a dense object causes gravitational time dilation, a phenomenon predicted by Einstein's general relativity, where time itself slows down in the presence of intense gravity, similar to, but not quite as extreme as, the effect near a black hole. The outer crust of a neutron star, though only a few kilometers thick, is one of the hardest substances in the universe, made up of an iron lattice interspersed with degenerate electrons. This rigid crust encases the unimaginable chaos beneath it. The temperatures here can reach hundreds of millions of degrees Kelvin, with some neutron stars, like RxJ 1856.5 3754, radiating at nearly 500,000 Kelvin even after millions of years. Beneath this crust lies an even stranger layer, nuclear pasta. Here, under crushing pressure, neutron-rich matter arranges itself into bizarre, spaghetti-like structures, forming the densest known material in the universe. Deeper still, the core is thought to consist of a superfluidic mass of bulk neutronium, where neutrons flow without resistance, generating effects that defy classical physics. Some theories even suggest that within the deepest reaches of the core, matter may transition into an exotic quark-gluon plasma, where individual neutrons and protons dissolve into their fundamental quark constituents. Neutron stars possess the strongest magnetic fields known in the cosmos. The conservation of angular momentum during the collapse dramatically amplifies the progenitor star's magnetic field, concentrating it into a volume thousands of times smaller. As a result, some neutron stars, known as magnetars, exhibit fields trillions of times stronger than Earth's, capable of distorting atomic structures and even influencing quantum vacuum fluctuations. These magnetic fields are responsible for a host of extreme astrophysical phenomena, from high-energy X-ray bursts to magnetar flares that release more energy in a fraction of a second than the Sun emits in 100,000 years. Not all neutron stars remain as quiet stellar corpses. If a neutron star is spinning rapidly and emits beams of radiation from its magnetic poles, it becomes a pulsar, one of the most extraordinary cosmic lighthouses. As the neutron star rotates, these focused beams sweep across space, appearing as regular pulses of light when viewed from Earth. Some pulsars, like PSRJ 1748-2446 AD, spin at nearly 716 times per second, meaning their surfaces move at nearly a quarter of the speed of light. Pulsars are among the most precise clocks in the universe, their rotational periods so stable that they rival atomic clocks in accuracy. They have been used for a range of scientific applications, from testing general relativity to aiding in the search for gravitational waves. Some pulsars even exist in binary systems, spiraling toward companions in a cosmic ballet that provides invaluable insights into relativistic physics. Neutron stars are more than just relics of stellar deaths. They are laboratories of the extreme, where physics is pushed to its absolute limits. Their immense densities, powerful magnetic fields, and relativistic phenomena make them crucial to our understanding of the fundamental forces governing the universe. They enrich galaxies with heavy elements, contribute to the cosmic web of radiation, and serve as cosmic signposts, guiding our understanding of gravity, quantum mechanics, and the nature of matter itself. Through the lens of modern astronomy, these exotic stellar remnants continue to unveil secrets of the universe, one pulsating beacon at a time. Within the extreme environment of a neutron star's magnetosphere, charged particles are forced to follow the paths dictated by intense magnetic field lines, riding along flux lines as they are funneled toward the star's polar caps. However, upon reaching these regions, they experience rapid repulsion, resulting in their expulsion at relativistic velocities. This acceleration process induces the emission of synchrotron radiation, which manifests predominantly in the radio wavelengths of the electromagnetic spectrum. One of the most fascinating aspects of pulsars is their role as cosmic lighthouses. The misalignment between a neutron star's rotational axis and its magnetic poles causes these beams of radio energy to sweep across space, much like the spinning beacon of a lighthouse. If Earth happens to be in the path of these periodic emissions, we observe them as highly regular pulses of radio waves. The first confirmed evidence of neutron stars in nature emerged through the detection of these pulsating radio signals. This breakthrough occurred in 1967 when Jocelyn Bell Burnell, a postgraduate student at the University of Cambridge, detected a series of galactic pulses occurring precisely 1.3 seconds apart. The discovery initially baffled the scientific community, with some even entertaining the possibility that the signals were artificial in origin, perhaps communications from an extraterrestrial intelligence. However, as more such signals were identified, including one emanating from the heart of the Crab Nebula, a natural astrophysical explanation began to gain traction. Theorists soon converged on the idea that these rapid radio pulses originated from rotating neutron stars. Their compact nature, extreme densities, and rapid spin rates made them the only viable explanation for such precise, high-frequency emissions. Since then, radio pulsars have become one of the most well-documented classes of neutron stars, with over 3,200 pulsars catalogued across the Milky Way. However, given the estimated number of supernovae that have occurred over the 13.6 billion-year history of our galaxy, it is believed that at least 1 billion neutron stars still exist within the Milky Way, and countless more in galaxies beyond. Most of these, however, have long since cooled and slowed, making them undetectable to us. Neutron stars, particularly pulsars, are at their most energetic in the first million years following their formation in a supernova. If a pulsar exists in isolation, meaning it lacks a significant stellar companion, its fate is sealed by a gradual loss of rotational momentum. This spin-down process occurs as the pulsar radiates energy in the form of gravitational waves and electromagnetic radiation. The immense magnetic field of the pulsar interacts with the surrounding space, dragging and distorting it. Over time, this interaction transfers kinetic energy away from the star's rotation, resulting in a progressive slowdown of its spin rate. This spin-down process governs the diverse spectral emissions of neutron stars. Younger, more energetic pulsars predominantly emit radio waves, while older and more evolved neutron stars, particularly those in binary systems, can also emit in X-ray and gamma-ray wavelengths. However, for a neutron star to sustain high-energy emissions in the X-ray and gamma-ray range, it typically requires an external source of energy replenishment, namely a nearby stellar companion from which it can accrete mass. In binary star systems, this process enables neutron stars to reignite and sustain their high-energy emissions, leading to the formation of millisecond pulsars and X-ray pulsars, objects that challenge our understanding of extreme physics and the life cycle of neutron stars. From their discovery in the 20th century to their role in modern astrophysics, pulsars have not only confirmed the existence of neutron stars, but have also become cosmic laboratories for testing the laws of physics. These extreme remnants continue to illuminate the mysteries of stellar evolution, relativity, and magnetism, providing insights into some of the most fundamental forces shaping our universe. X-ray binary pulsars, the powerhouses of stellar accretion. In some cases, a neutron star does not remain isolated, but instead resides within a binary system where it shares its cosmic dance with a stellar companion. This companion, which may be a white dwarf, red giant, or even a sun-like star, continuously sheds material into space, forming an accretion disk around the neutron star. As the neutron star gravitationally siphons matter from this disk, the infalling material not only increases the neutron star's mass, but also transfers angular momentum, accelerating its spin in a process known as spinning up. These pulsars, fueled by accretion, are classified as accretion-powered pulsars or X-ray pulsars, named for their prolific emission in the X-ray spectrum. As matter from the accretion disk is funneled onto the neutron star's surface, electrons become highly energized within its intense magnetic field. These electrons spiral along field lines before slamming into the star's polar caps, where they decelerate, releasing vast amounts of X-ray radiation in the process. These emissions, concentrated into narrow beams, rotate along with the neutron star, much like the sweeping searchlight of a radio pulsar. However, unlike standard radio pulsars, which predominantly slow down over time, X-ray pulsars can exhibit both spin-up and spin-down behavior, and in some instances, they maintain an astonishingly stable rotation rate over extended periods. If the neutron star's companion is a low-mass star, such as a small red dwarf or a white dwarf, the system is classified as a low-mass X-ray binary. Conversely, if the donor star is a massive and unstable red or yellow giant, the system is designated as a high-mass X-ray binary. In both scenarios, accretion fuels the neutron star, accelerating it to extreme rotational speeds, reaching hundreds of revolutions per second. Millisecond pulsars, the fastest rotating neutron stars. When a pulsar's rotation period drops below 10 milliseconds, meaning it completes more than 100 full spins per second, it is classified as a millisecond pulsar. Also referred to as recycled pulsars, these objects represent the fastest spinning neutron stars in existence, having been spun up to near relativistic speeds by prolonged accretion. At such staggering rotational velocities, they emit exquisitely regular and precise pulses, making them valuable tools for astrophysical measurements. The incredible stability of these pulses allows astronomers to detect even the slightest perturbations in their signals. For instance, the first exoplanets ever discovered, found in 1992 around the millisecond pulsar PSRB 1257+12, were detected through minute Doppler shifts in its pulse timing. These planets remain among the smallest known exoplanets to this day, with sizes and masses comparable to Earth's moon. The discovery of the first millisecond pulsar, PSRB 1937+21, in 1982 marked a turning point in neutron star astrophysics. Spinning at an astonishing 641 revolutions per second, it held the record as the fastest known pulsar for decades. However, a more extreme object was later identified, PSR J1748-2446 AD, located within the dense stellar environment of Thorne-Zytkow 5. Rotating at a breathtaking 716 times per second, this pulsar's equatorial surface races through space at approximately a quarter of the speed of light. These hyperfast neutron stars are often found in globular clusters, densely packed stellar environments containing tens or even hundreds of thousands of ancient stars. In such close quarters, binary interactions are common, leading to an unusually high incidence of millisecond pulsars. The clusters Thorne-Zytkow 5 and 47 Tucanae hold the records for the most known millisecond pulsars, boasting 37 and 22 respectively. Despite their extreme spin rates, millisecond pulsars do not necessarily host the strongest magnetic fields in the universe. A neutron star's magnetic field strength is largely dictated by its age and progenitor star type, rather than solely by its rotation speed. Certain progenitor stars, such as the recently discovered massive magnetic helium star HD 45166, exhibit fields exceeding 100,000 times that of Earth. When such a star undergoes core collapse, its already powerful magnetic field is amplified exponentially, giving rise to the most magnetized objects in existence, magnetars. These extreme neutron stars possess fields trillions of times stronger than Earth's, capable of distorting atomic structures, altering the vacuum of space, and releasing bursts of energy so powerful that they can temporarily disrupt radio communications on Earth from thousands of light years away. As such, magnetars represent the pinnacle of neutron star evolution, bridging the gap between the already extreme properties of pulsars and the even more mysterious realms of quantum physics and general relativity. From accretion-powered X-ray pulsars to the lightning-fast millisecond pulsars and the unfathomable power of magnetars, neutron stars continue to test the limits of modern physics. As we probe deeper into these enigmatic objects, we may yet uncover new insights into the fabric of the universe itself. Magnetars, the titans of stellar magnetism. The tale of these extraordinary cosmic entities begins in 1979, when astronomers first detected an enigmatic burst of gamma radiation originating from the Large Magellanic Cloud. Unlike conventional gamma-ray bursts, this signal exhibited slightly longer wavelengths, what scientists would later call soft gamma rays, before fading into obscurity for 2 months. Then, on March 5th of that same year, the enigmatic source returned, producing one of the most luminous gamma-ray outbursts ever recorded, unleashing in a mere fifth of a second an amount of energy equivalent to 1,000 years of solar output. While neutron stars were the immediate suspects, the peculiar softness of the gamma rays and the repeating nature of the outbursts defied the behavior of conventional neutron stars. By the end of the year, 3 distinct instances of these emissions had been identified, earning them the designation soft gamma-ray repeaters. These objects exhibited periodic flashes of low-energy gamma rays that would persist for about a week before fading into dormancy, sometimes for months, even years. Yet, each active phase provided crucial insights into their underlying mechanisms, particularly their rotation rates and spin-down behavior, enabling scientists to infer their magnetic field strengths. To their astonishment, all 3 objects exhibited field strengths on the order of hundreds of trillions of Gauss, with some estimates exceeding a quadrillion Gauss, a staggering 2 quadrillion times stronger than Earth's magnetic field. These were not merely extreme neutron stars. They were the most magnetized objects ever discovered in the universe, operating at the very limits of efficiency for a spinning, radiating stellar core. Around the same time, astronomers began detecting another class of peculiar signals, this time in the X-ray spectrum. Unlike conventional accretion-powered X-ray pulsars, these objects emitted short, high-energy X-ray bursts that exhibited anomalous behavior. Over time, it became increasingly clear that these anomalous X-ray pulsars shared striking similarities with the soft gamma-ray repeaters, hinting at a common astrophysical origin. Both classes of objects exhibited extreme outbursts, transient flares, and irregular decay patterns, leading scientists to propose a new classification, magnetars. The term, coined in the early 1990s, described neutron stars with magnetic fields so strong that they could drive some of the most violent and energetic processes ever observed in the cosmos. Despite their extraordinary power, magnetars appear to be exceptionally rare, with only about 25 known examples in the Milky Way. Their scarcity likely stems from the fact that they represent a brief, transitional phase in the evolution of highly magnetized neutron stars. During this phase, a magnetar's magnetic field undergoes rapid decay, generating a host of extreme astrophysical phenomena, including magnetic reconnection events, megaflares, and intense X-ray and gamma-ray bursts. Magnetars exist in a realm beyond our typical understanding of stellar remnants. With magnetic fields trillions of times stronger than Earth's, they exert forces so extreme that they can distort atomic structures, alter the very fabric of space-time, and generate some of the most intense high-energy emissions in the universe. These objects are ticking time bombs of magnetic instability, periodically unleashing bursts that momentarily rival the brightness of entire galaxies. Starquakes, the tremors of a magnetar's fury. As dead stars rotate, their metallic crusts endure ceaseless torment, pressed between the immense forces acting from within and without. Beneath the surface, swirling currents of superfluid neutronium generate staggering electrical fields, while above, the twisting and dragging of intense magnetic field lines exert enormous tension. Over time, this relentless stress proves too much for the crystalline crust of the neutron star. Eventually, it cracks, just slightly, shifting by mere micrometers toward a more spherical configuration. But in the world of magnetars, even such imperceptible shifts can unleash some of the most violent electromagnetic events in the cosmos. These seismic readjustments, known as starquakes, release torrents of electromagnetic radiation, including bursts of high-energy X-rays and soft gamma rays. The most extreme starquake ever recorded occurred on December 27, 2004, when the magnetar SGR 1806-20 produced an eruption so powerful that in under 1 second, it emitted more gamma ray energy than our Sun generates in 150,000 years. Despite the fact that this event occurred over 40,000 light-years away, its impact was still felt on Earth. The trailing shockwaves of radiation were so intense that they caused a detectable increase in ionization levels in our planet's upper atmosphere. Had such an outburst occurred within 10 light-years of Earth, the consequences would have been nothing short of catastrophic. The immense gamma radiation would have completely eroded our magnetic field, leaving the planet exposed to the full onslaught of solar radiation. This, in turn, would have boiled away the oceans, stripped the atmosphere, and transformed Earth's surface into a parched, irradiated wasteland, a world bereft of life. Yet gamma rays are not the only emissions thought to arise from starquakes. Some researchers have proposed that these seismic events may also be a potential source of fast radio bursts, brief yet highly energetic radio pulses that have baffled scientists since their discovery. To date, over 700 of these enigmatic signals have been recorded with no definitive explanation for their origin. Intriguingly, at least 30 of these FRBs are classified as repeaters, signals that, while not constant, appear sporadically from the same location. This recurrence suggests a possible link between FRBs and magnetar activity, drawing a potential parallel to the soft gamma-ray repeaters emitted by these stars. Alternatively, some astrophysicists speculate that fast radio bursts might be produced during the violent collisions of neutron stars. In such catastrophic mergers, two ultra-dense stellar remnants crash together and consume one another, unleashing yet another level of cosmic devastation. The resulting explosions and gravitational distortions could, in turn, generate bursts of radio waves that propagate across the universe, carrying with them the faint echoes of their cataclysmic origins. Whatever their true cause, starquakes and the bursts they produce remain some of the most extreme astrophysical phenomena in existence. As observational techniques improve, future discoveries may bring us closer to unraveling the mysteries of these stellar tremors, shedding light on the inner workings of the most magnetic and volatile objects in the universe. The fastest spinning pulsars are not just celestial timekeepers. They serve as remarkably precise indicators of their surrounding environment. This property led American physicists Joseph Taylor and Russell Hulse to make a groundbreaking discovery in the early 1970s, earning them the 1993 Nobel Prize in Physics. Their work on the pulsar PSRB 1913+16, a rapidly spinning neutron star locked in a binary system with a slower, cooler neutron star companion, provided the first indirect observational evidence for gravitational waves, a phenomenon predicted by Albert Einstein nearly 80 years earlier. By measuring the Doppler shifts in the pulsar signal, Taylor and Hulse demonstrated that the two neutron stars were spiraling ever closer together, losing energy through the emission of gravitational waves, invisible ripples in the very fabric of space-time. It would take another 30 years before humanity would achieve the first direct detection of these waves in 2015, using the Laser Interferometer Gravitational Wave Observatory. When two compact stellar remnants, whether black holes, neutron stars, or a combination of both, spiral toward each other, their orbital velocities increase to astonishing levels, eventually reaching speeds of 2/3 the speed of light. The rapid motion of these dense objects distorts and stretches spacetime, releasing a final crescendo of gravitational waves that ripple outward across the cosmos. These signals, detected by LIGO and other observatories, often precede a cataclysmic merger, allowing astronomers to pinpoint the precise location of these cosmic collisions. As the neutron stars draw closer, the extreme gravitational forces cause them to deform, their iron-rich crusts rupturing as they near their inevitable collision. At the moment of impact, an enormous explosion occurs, scattering fragments of neutron-rich material into space and briefly exposing the shattered cores of these stellar remnants to the near vacuum of space. This event is known as a kilonova, one of the most energetic and transformative astrophysical phenomena in the universe. The crucible of heavy elements, how kilonovae forge the building blocks of planets and life. Much like a supernova, a kilonova is an extreme explosion that produces vast amounts of heavy elements. But unlike a supernova, which primarily synthesizes elements up to iron, kilonovae are responsible for the formation of the heaviest elements in the periodic table. As neutron-rich ejecta are violently expelled into space, nuclear reactions known as the R process and P process take place, enabling the synthesis of elements such as gold, platinum, uranium, and thorium. Substances crucial not only for planetary formation, but also for the chemistry of life itself. For decades, astronomers believed that supernovae were the primary factories of heavy elements. However, recent discoveries suggest that kilonovae contribute the lion's share of these essential building blocks, enriching the interstellar medium with the raw materials needed to form planets, moons, and even organic molecules. Just as supernovae are associated with long-duration gamma-ray bursts, which last anywhere from a few seconds to several minutes, kilonovae produce their own class of GRBs. These short gamma-ray bursts last 2 seconds or less, a result of the brief exposure of the neutron star's shattered interiors to space. In some cases, kilonovae also emit fast radio bursts, anomalous, highly energetic radio pulses whose origins remain enigmatic. The remnants of the two neutron stars rapidly collapse into a single composite object, with its fate dependent on the combined mass of the merging bodies. If the total mass exceeds 2.5 to 3 times the mass of the Sun, gravitational collapse continues unabated, resulting in the formation of a new black hole. If the mass falls below this threshold, the merged body stabilizes into a newly formed, heavier pulsar, or perhaps a magnetar, reigniting the evolutionary cycle of neutron stars. However, if the mass lies precariously between these two extremes, an entirely different scenario may unfold. If the post-merger remnant is massive enough to overcome neutron degeneracy pressure, the force preventing neutrons from collapsing under their own gravity, but not quite massive enough to reach black hole status, then the result is a boundary object, teetering on the edge of known physics. Under these incomprehensible pressures, neutrons themselves dissociate into their fundamental quark components, potentially forming an exotic quark star, an entity whose structure may resemble the extreme conditions of the early universe moments after the Big Bang. Neutron star mergers offer a rare, natural laboratory for probing these extremes of matter and energy, allowing scientists to test the limits of general relativity, nuclear physics, and quantum chromodynamics in ways previously unimagined. The discovery of such boundary objects could reshape our understanding of the very nature of matter and space-time itself. The merging of neutron stars is more than just a spectacular astrophysical event. It is a cosmic alchemy, responsible for forging the heaviest elements, sculpting the interstellar medium, and shaping the very fabric of the universe. From the gravitational waves that ripple across space-time to the kilonovae that paint the cosmos with elemental richness, these collisions leave an indelible mark on the past, present, and future of the cosmos. Quark stars, the hypothetical realm of subatomic stellar remnants. Neutrons, the fundamental components of atomic nuclei, belong to a class of particles known as hadrons, composite subatomic particles made of quarks bound together by the strong nuclear force. Quarks are the most elementary building blocks of matter. They possess no internal structure and cannot be broken down further by pressure or heat. These elementary particles emerged in the primordial moments of the universe, when temperatures and densities were unfathomably high. However, as the universe expanded and cooled, free quarks coalesced into hadrons, forming the protons and neutrons that now constitute ordinary matter. Though free quarks are no longer found in nature, they could theoretically exist in an ultra-compressed state of matter, a scenario hypothesized to occur within a quark star. Such an object would form when an accreting neutron star approaches the Tolman-Oppenheimer-Volkoff limit, the critical threshold where gravitational collapse is strong enough to overcome neutron degeneracy pressure. In this extreme environment, the very structure of neutronium could break down, leading to quark deconfinement, a process in which neutrons themselves dissolve into a quark-gluon superfluid. This exotic state of matter, held apart by its own nuclear repulsion against gravity, would give the star a density comparable not to an atomic nucleus, but to a hadron-sized entity on a macroscopic scale. A two-flavor quark star, composed solely of up and down quarks, would resemble a neutron star in many ways, with a dense quark-gluon core surrounded by an outer shell of less pressurized nuclear matter. Its maximum diameter would likely be around 15 kilometers, akin to that of a typical neutron star. However, if a quark star were to contain an additional component, strange quarks, which belong to the second generation of fundamental particles, the composition of the star would be drastically altered. Strange quarks share the same charge as down quarks, yet their presence allows for additional nuclear conversions, potentially making the star significantly more stable in low-energy states. In fact, some theoretical frameworks propose that strange quark matter may represent the absolute ground state of matter at the highest densities, meaning that a three-flavor strange quark star would be self-bound, requiring no solid nuclear crust to maintain its integrity. Instead, it would possess a transient, fluctuating boundary, a thin interface where quark density abruptly falls to zero. In its early stages, a strange star would lack a solid outer crust. Over time, however, intense electrical currents emanating from its quark core would expel the remnants of normal nuclear matter, forming an ephemeral, decoupled shell. This outer layer would be short-lived, as periodic collapses back into the star would catalyze immense bursts of electromagnetic radiation, including gamma-ray flares. Such emissions have been proposed as a potential explanation for anomalous soft gamma-ray repeaters, high-energy bursts that deviate from conventional magnetar activity. Following each outburst, the bare strange quark core would once again be exposed to the vacuum of space, leading to a cyclical process of violent emissions. Furthermore, because strange quark matter is theoretically extremely stable, any fragments ejected from the star could persist indefinitely as free-floating particles, nuggets of strange quark matter known as strangelets. Despite their theoretical plausibility, quark stars and strange stars remain hypothetical, as no confirmed observational evidence has yet validated their existence. From a distance, these objects would likely be indistinguishable from conventional pulsars, making their identification extraordinarily difficult. While quark stars remain an intriguing possibility, future advancements in observational astrophysics may provide the key to their detection. Some astronomers speculate that objects like GOJ 165540, a known X-ray binary with unusual characteristics, could hint at the presence of a hybrid neutron-quark object. As research continues, instruments capable of resolving quark-level astrophysical signatures may someday provide empirical confirmation of these enigmatic stellar remnants. Thorne-Zytkow objects, the star within a star. Among the most enigmatic and rare stellar configurations ever theorized is the Thorne-Zytkow object, a peculiar hybrid star where a neutron star is engulfed by the immense envelope of a red giant. First proposed in 1977 by Kip Thorne and Anna Zytkow, these objects blur the line between conventional stellar evolution and extreme astrophysical phenomena, challenging our understanding of the interactions between compact remnants and their larger, living stellar companions. A prime candidate for such an origin story is the system formerly known as X-ray Nova Scotia 1994, a chaotic binary system located 10,000 light-years away. At its heart lies a small evolved F-type star, locked in a volatile gravitational dance with an unseen accreting companion, inferred to be a black hole several times the mass of the Sun. The unusual dynamics of this system, its tight orbital period and high velocities, suggest that both objects share a common progenitor, likely tracing their history back to a hybrid star that once hosted an infalling neutron star. Unlike typical binary interactions, where a neutron star may tidally disrupt or accrete matter from its companion, A TO emerges when a neutron star spirals inward into the extended envelope of a red giant. Rather than tearing its companion apart, the neutron star plunges beneath the giant's photosphere, sinking into its interior while remaining intact. This marks the formation of a true star within a star. Over the next few hundred years, the neutron star continues to migrate inward, pulling intense magnetic fields and gravitational perturbations through the plasma of its host. This interaction violently disrupts the delicate balance of the red giant's interior, causing instabilities in its core structure. Despite this turmoil, the object's external appearance remains largely indistinguishable from a conventional late-stage red giant, making direct detection an ongoing challenge. Within a TGO, the neutron star and the disturbed stellar core eventually enter a tight orbit, triggering a final, catastrophic merger. When this happens, the vast majority of the red giant's mass is funneled into the forming black hole, while its outer layers, now left without an internal energy source, collapse and disperse into space. However, not all of this material is lost to the abyss. It is hypothesized that some residual stellar matter survives, condensing into what is now observed as a curiously low-mass, evolved F-type star. This peculiar survivor, still orbiting and feeding the black hole, may provide an observational signature of past Thorne-Zytkow evolution. Beyond their sheer astrophysical intrigue, Thorne-Zytkow objects illustrate the profound and often unexpected contributions of neutron stars to the wider galactic ecosystem. Though these objects exert destructive gravitational forces, their dynamic interactions also enrich surrounding space with complex chemical elements, the raw materials necessary for planet formation and the emergence of life. In this sense, neutron stars, despite their seemingly hostile and inexorable nature, have played a vital role in shaping the universe as we know it. Their interactions, whether through supernovae, binary mergers, or the creation of objects like TOs, have helped seed galaxies with the ingredients essential for organic chemistry and planetary development. Thus, the discovery of such objects may be just as significant to modern astrophysics as it would have been had the first pulsar signal, LGM-1, truly been an interstellar transmission from extraterrestrial intelligence. In the grand scheme of cosmic evolution, these fascinating stellar remnants continue to illuminate the unknown, shaping the very conditions that make life possible. And with that, we close this chapter on the unfathomable complexity of the cosmos. Have you ever wondered how far humanity could go in its pursuit of knowledge? Could we, as a civilization, ever overcome the ultimate boundaries of existence? What happens when even the most advanced technology fails to answer the fundamental questions of reality? These are the mysteries that have haunted thinkers for centuries and continue to challenge us today. Imagine a civilization so advanced that it spans galaxies with technologies capable of capturing every wavelength of light from the farthest corners of the observable universe. A civilization that has unlocked the secrets of the quantum realm, colonized countless star systems, and reshaped entire galaxies to suit its needs. And yet, despite their unimaginable power, they find themselves unable to answer one of the most profound questions. Are they truly alone in the cosmos? This is the story of the great arc ships, colossal vessels that carry the dreams and ambitions of a civilization reaching for the stars. But as their journey unfolds, they realize that the universe they inhabit is just one of infinitely many. What does it mean to confront infinity? Can any civilization, no matter how advanced, grasp the scale of an infinite multiverse? And if they can't, what is the ultimate limit of knowledge? These questions set the stage for an extraordinary tale of exploration, despair, and discovery. A story of how a civilization, in its relentless pursuit of answers, discovers not only the vastness of the cosmos, but also the boundaries of their own understanding. So how far could we go? How much could we ever truly know? The infinite multiverse. It began as a whisper among their greatest minds, an idea so radical that many dismissed it outright. For eons, the civilization had looked upon their universe as the ultimate arena of existence. Vast, incomprehensibly large, yet singular. They had built galaxy-spanning observatories, devices so sensitive they could detect even the faintest remnants of light from the birth of their cosmos. They had peered into the quantum realm, uncovering particles and forces that danced on the edge of reality. Their arc ships had traveled across intergalactic voids, bridging the unimaginable distances between galaxies. Yet, despite these monumental achievements, something remained elusive. The realization came not from one breakthrough, but from a convergence of discoveries across disciplines. Slowly, piece by piece, the evidence pointed to a staggering conclusion. Their universe was not alone. It was but one in a vast multiverse, an infinite collection of universes, each with its own set of physical laws, its own histories, and its own possibilities. At first, the idea was exhilarating. The multiverse promised a playground of infinite variety. If one universe could give rise to life and intelligence, how many more might teem with civilizations beyond their imagination? If their own cosmos held wonders and mysteries, what untold marvels might lie in the realms beyond? It seemed as though the multiverse was the ultimate frontier, a boundless expanse of exploration and discovery. But as they delved deeper into the implications, the exhilaration gave way to unease, and unease to despair. The multiverse was not just infinite in its scope, it was infinite in every possible way. For every universe that mirrored their own, there were countless more, where the laws of physics rendered stars impossible, or where time flowed in directions incomprehensible to their minds. For every universe that harbored intelligent life, there were infinite others that were empty and barren. This infinity posed a paradox. In a finite universe, questions like, "Are we alone?" could theoretically be answered with enough exploration and data. But in an infinite multiverse, such questions became meaningless. Any finite amount of information they could gather was dwarfed by the endless unknown. Were they a common occurrence or a rare anomaly? Did life like theirs make up 1% of all universes or 99%? The numbers lost all significance in the face of infinity. Their calculations always returned the same result: 0. Not because they lacked knowledge, but because no amount of knowledge could ever make a dent in the infinite. The multiverse rendered probabilities irrelevant. For every possibility they could imagine, there existed infinite universes where it was true, and infinite universes where it wasn't. This realization was not just an intellectual challenge, it was an existential one. It forced them to confront the limits of their understanding. Their entire civilization, the most advanced in the history of their cosmos, was reduced to a single, insignificant data point in an ocean of infinity. The multiverse was a mirror reflecting not their achievements, but their insignificance. And so, they were left with an impossible question. How do you measure yourself against the infinite? How do you find meaning in a sea where every discovery is drowned by countless unknowns? The multiverse was no longer a frontier to conquer. It was a reminder of their ultimate limitations, a vast, uncaring expanse that would forever lie beyond their grasp. The civilizational journey. In the beginning, the civilization's journey was like many others, a story of curiosity and survival. They were once beings confined to their homeworld, gazing at the stars with wonder. The celestial patterns above them inspired awe and questions. What were those points of light? Were they gods, guiding their fate, or were they destinations waiting to be reached? Slowly, over centuries, their curiosity evolved into something more structured, an organized effort to understand the world around them. They developed tools and methods, and from those humble beginnings, their path to greatness was set. At first, their discoveries were simple, yet transformative. They learned to harness fire, to farm, and to build shelters. These advancements allowed them to escape the precariousness of survival and turn their focus outward. They began to study the heavens, charting the movements of the stars, the cycles of the moon, and the rhythms of the seasons. Over generations, this knowledge became the foundation of their civilizations, influencing their myths, religions, and early sciences. As their understanding grew, so too did their ambitions. They invented devices to extend their senses, telescopes to peer into the cosmos, and microscopes to uncover the hidden details of their world. The scientific method emerged, giving them a way to systematically explore the unknown. Questions that had once seemed insurmountable were now within their reach, and the pace of discovery quickened. Over centuries, they unlocked the secrets of gravity, energy, and matter, piecing together the laws that govern the universe. The next great leap came when they turned their gaze from the sky to their own world, realizing they could harness its energy. They built machines powered by steam, then electricity, and eventually, nuclear fusion. These advancements propelled them into the industrial age, where their mastery over energy and materials transformed their societies. They became a Kardashev Type 1 civilization, fully harnessing the power of their planet. But they did not stop there. With the resources of their world secured, they turned their attention outward to the vast expanse of space. They constructed rockets and launched probes, sending them to explore their neighboring planets. They established colonies on moons and distant worlds, transforming barren landscapes into habitable environments. Their solar system became a sprawling network of outposts, research stations, and industrial hubs. The move from a planetary civilization to a star-faring one marked a turning point in their history. They began to dream of the stars, not as distant lights, but as destinations. They developed technologies to harness the energy of their sun, constructing Dyson swarms, vast arrays of solar collectors that captured its immense power. With this energy, they built arc ships, colossal vessels capable of carrying entire populations across interstellar distances. These arc ships were not just tools of exploration, they were self-sustaining ecosystems, capable of surviving journeys lasting thousands or even millions of years. Inside, their passengers lived, worked, and thrived, carrying the hopes of their civilization to distant star systems. Some of these voyages succeeded, establishing new colonies in other parts of the galaxy. Others were lost to the void, their fates unknown. But the civilization pressed on, undeterred by the risks. As they expanded into the stars, their understanding of the universe deepened. They built particle colliders that spanned entire solar systems, smashing matter together at unimaginable energies to uncover the building blocks of reality. They constructed telescopes so powerful that they could peer billions of years into the past, observing the birth of galaxies and the first moments of the cosmos. They developed quantum computers capable of simulating entire star systems, predicting their behavior with stunning accuracy. Yet, as their knowledge grew, so too did their realization of the universe's complexity. The more they learned, the more they understood how little they truly knew. Mysteries like dark matter, dark energy, and the unification of quantum mechanics and gravity remained unsolved. These barriers loomed like unscalable mountains, challenging their belief that all questions could eventually be answered. Despite these obstacles, they continued to push the boundaries of what was possible. They reached the level of a Kardashev Type 2 civilization, harnessing the energy of entire stars. They transformed entire solar systems into interconnected hubs of activity, using their immense resources to fuel their insatiable quest for knowledge. Black holes became their power sources, their immense gravitational energy driving experiments that probed the very fabric of space-time. However, the limits of their understanding became increasingly apparent. They discovered that some questions might never be answerable, not because they lacked the tools or the will, but because the nature of reality itself imposed barriers. The universe, they realized, was not infinite in its accessibility. There were regions of space-time they could never reach, events they could never witness, and questions they could never fully resolve. The greatest challenge came when they began to theorize about the multiverse. This idea, born from their exploration of quantum mechanics and cosmology, suggested that their universe was just one of infinitely many. Each universe in this multiverse had its own unique set of physical laws, its own history, and its own possibilities. The implications of this discovery were staggering. If the multiverse were real, it rendered many of their questions meaningless. How could they measure their place in the cosmos when the cosmos itself was infinite? How could they calculate probabilities or understand their uniqueness when every possibility existed somewhere? This realization cast a shadow over their achievements. They had explored the stars, reshaped galaxies, and unlocked many of the universe's secrets, yet they found themselves dwarfed by the enormity of the multiverse. Their entire civilization, the most advanced in the history of their universe, was reduced to a single data point in an infinite sea. No matter how far they went, no matter how much they discovered, there would always be questions they could never answer. For all the barriers they faced, they refused to give up on their quest for understanding. They believed that the pursuit of knowledge, even in the face of infinity, was itself a form of meaning. Their story was not just about the answers they found, but about the relentless drive to explore, to question, and to grow. In this, they found purpose. Their journey was far from over, and as they stared into the infinite expanse of the multiverse, they carried with them the hope that somewhere, somehow, they might discover not only the secrets of the cosmos, but also the ultimate truth about themselves. Biological and technological limitations. For all their monumental achievements, the civilization was haunted by an undeniable truth. Their very essence was shaped by their biological origins. Their intelligence, creativity, and capacity for curiosity, while extraordinary, were limited by the finite structure of their minds and bodies. Their brains, evolved for survival on a single planet, were astonishingly complex but fundamentally constrained. They could process only so much information at a time, and their perceptions were narrow, limited to a small slice of reality defined by their senses. Memory was imperfect, prone to fading or distortion over time. Their physical bodies were fragile, requiring food, water, rest, and protection from the harshness of the universe. Even their lifespans, though extended by technological advancements, were mere moments on the cosmic timescale. How could beings with such constraints hope to grasp the infinite mysteries of the cosmos? To push beyond these limitations, they turned to technology. At first, they sought to augment their biology. Cybernetic enhancements improved their physical resilience, extended their lifespans, and expanded their cognitive capacities. Neural interfaces allowed them to connect directly to computational networks, accessing vast reservoirs of knowledge in real time. For many, the line between the organic and the synthetic began to blur. As their ambitions grew, they took the next step, escaping the confines of biology entirely. Entire generations transitioned into digital consciousness, uploading their minds into immense computational systems. In these virtual domains, thought was no longer bound by the constraints of neurons and synapses. They could process information at unimaginable speeds, simulate entire worlds, and explore concepts that their biological counterparts could scarcely comprehend. Yet even in this new form, they encountered barriers. Their original biological frameworks, the product of millions of years of evolution, continued to shape their perceptions and thought processes. No matter how advanced their systems became, they were still rooted in the biases and limitations of their creators. Artificial intelligences, designed to think beyond human constraints, often mirrored the priorities and blind spots of those who built them. Though faster, more efficient, and more powerful, these machines were not as free from limitation as they had hoped. Their technological triumphs brought them closer to the cosmos's most elusive mysteries, but also exposed new challenges. In their exploration of the quantum realm, they encountered the Heisenberg uncertainty principle, which limited their ability to precisely measure fundamental particles. They discovered that no matter how advanced their tools became, there were aspects of the universe that could not be fully known. The deeper they delved into the subatomic world, the more it seemed to resist their efforts to map it completely. On a cosmic scale, the limitations were equally daunting. The vastness of space and the finite speed of light meant that many regions of the universe were forever beyond their reach. Even as they colonized galaxies and harnessed the energy of entire star systems, they were bound by the unyielding laws of nature. They could see the universe's grand design, but only from a narrow vantage point defined by their own perspective. Despite these challenges, they refused to accept their limits as final. They developed artificial intelligences with radically different architectures, hoping to create systems that could think in ways fundamentally alien to their own. These intelligences were not meant to replace them, but to complement their understanding, providing insights into aspects of the universe their own minds could not grasp. Yet, even these new systems, for all their brilliance, seem to reflect the boundaries of the civilization that created them. The civilization also experimented with genetic engineering, modifying their biology to enhance their cognitive and physical abilities. They created entirely new forms of life, tailored to survive in extreme environments and think in ways no organic mind ever could. These creations, while extraordinary, were still extensions of the same fundamental desire to overcome the barriers that separated them from the ultimate truths of existence. As they pressed onward, their quest became as much about understanding themselves as it was about understanding the universe. They sought not only to push the boundaries of their knowledge, but to redefine what it meant to be alive, to think, and to explore. Each breakthrough brought new possibilities, but also new questions about the nature of intelligence, consciousness, and the limits of knowledge itself. Their journey through the cosmos had shown them that no matter how powerful their technology became, they would always be bound by some form of limitation, whether biological, technological, or imposed by the universe itself. Yet it was this very struggle that defined their identity. They were a civilization driven by the relentless pursuit of understanding, determined to push past every barrier, no matter how insurmountable it seemed. And so they pressed on, their efforts fueled by the hope that somewhere beyond the horizon they might find the answers they sought, or perhaps something even greater. Interstellar and intergalactic expansion. Faced with the limitations of biology, technology, and the boundaries of the known universe, the civilization turned its attention to the stars. They understood that to overcome these constraints, they needed to expand their reach far beyond their home systems. Their gaze shifted from the confines of their galaxy to the endless expanse of interstellar and intergalactic space. This was not just a journey of survival, but a mission to unlock the secrets of existence itself. The civilization's interstellar efforts began with their arc ships, massive vessels designed to carry entire populations across the gulfs of space. These were no ordinary spacecraft. They were self-sustaining ecosystems capable of enduring journeys that spanned millennia. Inside, passengers lived in suspended animation, their biological needs reduced to the bare minimum, while advanced artificial intelligences piloted the ships through the cosmic void. These journeys were not without risks. Many ships vanished, swallowed by the darkness between the stars, their fate unknown. Yet for every ship lost, others succeeded, planting colonies in distant systems and extending the reach of their civilization. Over time, their methods of travel evolved. They built immense light sails, propelled by powerful beams of energy from home systems, allowing smaller, faster crafts to leap across vast distances. They developed wormhole technologies, creating shortcuts through space-time itself, though these remained experimental and fraught with dangers. For the most distant targets, they relied on generational ships, massive habitats where entire societies lived, worked, and died during the long journey to a new star. Their intergalactic expansion posed even greater challenges. While they had mastered the energy of entire stars, moving between galaxies required energy on an almost incomprehensible scale. To overcome this, they constructed Dyson swarms around dying stars, capturing every last watt of energy to fuel their intergalactic voyages. They also learned to harness the rotational energy of black holes, extracting power from the very fabric of space-time. With these advancements, they launched expeditions to neighboring galaxies, reaching the edges of the known universe. Communication between these far-flung colonies became an insurmountable obstacle. The vast distances introduced delays measured in centuries or millennia, making real-time coordination impossible. Each colony became its own autonomous entity, adapting to the unique challenges of its environment. Despite this, they remained united by a shared purpose: the pursuit of knowledge. Information from every corner of their civilization was collected, analyzed, and shared, creating a tapestry of understanding that spanned the stars. As they ventured deeper into the cosmos, they encountered not only physical challenges, but philosophical ones. What did it mean to expand endlessly into the void? Were they driven by a genuine desire to explore, or were they fleeing the realization of their own limitations? The infinite multiverse loomed over their efforts, reminding them no matter how far they traveled, they could only ever explore a finite portion of infinity. Their expansion also brought them closer to the mysteries they sought to solve. They observed the structures of the cosmos on an unprecedented scale, uncovering patterns in the distribution of galaxies and dark matter that hinted at deeper laws of nature. They built observatories that could detect the faint whispers of gravitational waves from the earliest moments of the universe, capturing echoes of creation itself. Each discovery brought them closer to understanding the nature of reality, but also revealed how much they still didn't know. As their civilization stretched across galaxies, they began to sense the looming shadow of the ultimate limits. They had conquered vast distances, harnessed incredible energies, and built a network that spanned the stars, but they were still bound by the fundamental laws of physics. The speed of light, the decay of information over time, and the relentless march of entropy placed boundaries on their reach. The expansion set the stage for a profound reckoning. They had reached the threshold of their capabilities, standing on the precipice of the unknown. Beyond lay the cosmic limits, the unobservable regions of the universe, the mysteries of black holes, and the boundaries imposed by quantum mechanics. These would define their next great challenge and lead them into the most difficult questions of all. What lies beyond what can be known? And how far could even the most advanced civilization go before it must confront the boundaries of the universe itself? Cosmic limits. As the civilization pushed the boundaries of its interstellar and intergalactic expansion, it became increasingly clear that the universe itself imposed fundamental limits. For all their ingenuity and technological prowess, there were barriers they could not cross, horizons they could not reach, and mysteries that resisted every effort to unravel. These cosmic limits, embedded in the fabric of reality, defined the ultimate challenges of their existence. One of the first and most immutable boundaries they encountered was the speed of light. This universal constant dictated not only the pace of their interstellar voyages, but also the limits of their communication and observation. No matter how advanced their propulsion systems became, the distances between galaxies meant that travel was measured in millennia, even for their fastest ships. The information sent from one end of their empire to another was hopelessly delayed, making real-time coordination across vast cosmic distances impossible. Light, traveling at its constant speed, could only traverse so far in the 13.8 billion years since the universe's birth. This created a cosmic horizon, the observable universe, that defined the furthest reaches of what they could ever see or measure. Beyond this horizon lay regions of space and time forever inaccessible to them, not because they lacked the technology, but because the universe itself had not yet allowed its light to reach them. Even within the observable universe, they faced another immutable limit, the expansion of the cosmos. The discovery of dark energy revealed that the universe was not just expanding, but accelerating in its growth. Over time, galaxies at the edge of the observable universe would recede faster than the speed of light, slipping beyond their view and taking with them any chance of interaction or observation. The universe, for all its vastness, was becoming increasingly isolated, fragmenting into unreachable islands of matter. Their efforts to probe the quantum realm brought them face to face with another barrier, the Heisenberg uncertainty principle. This fundamental feature of quantum mechanics made it impossible to simultaneously measure certain pairs of properties, like the position and momentum of a particle, with absolute precision. No matter how advanced their instruments became, they could never escape this inherent fuzziness at the smallest scales. The quantum realm remained a domain of probabilities and uncertainties, defying their desire for absolute knowledge. Black holes presented perhaps the most tantalizing and frustrating of cosmic limits. These objects, formed from the collapse of massive stars or the merger of galaxies, were perfect keepers of secrets. Their event horizons marked a one-way boundary. Once crossed, nothing, not even light, could escape. Everything that fell into a black hole became hidden from the universe outside, leaving only its mass, spin, and charge as observable properties. The information about what the black hole had consumed seemed to vanish, leading to one of the great paradoxes of modern physics, the black hole information paradox. For the civilization, black holes were both a source of fascination and despair. They built observatories to study these enigmatic objects, seeking clues about the nature of space-time and gravity. They even attempted to approach the event horizon, sending probes to gather data from the brink of the unknown. But the closer they came, the more they realized that the answers they sought were locked away, perhaps forever. The singularity at the heart of a black hole, where all known laws of physics broke down, represented a boundary they could neither cross nor fully understand. Another limit loomed even larger: entropy. The second law of thermodynamics dictated that the universe tended toward greater disorder, a relentless march toward a state of maximum entropy. Over unimaginable timescales, stars would burn out, galaxies would dissolve, and black holes would evaporate. The universe, once vibrant and full of structure, would fade into a cold, dark expanse, a state known as heat death. This ultimate fate imposed a temporal boundary on their existence, forcing them to confront the reality that even their most advanced technologies and civilizations were impermanent. Despite these barriers, the civilization did not surrender to despair. They saw each limit not as an end, but as a challenge to be understood and navigated. They probed the edges of the observable universe, seeking patterns in the distribution of galaxies that might hint at what lay beyond. They developed theories to explain the nature of dark energy and attempted to find ways to manipulate it, hoping to slow or reverse the universe's accelerating expansion. Their experiments in quantum mechanics grew increasingly ambitious. They explored the phenomenon of quantum entanglement, where particles separated by vast distances could remain mysteriously connected, sharing information instantaneously. While they could not break the speed of light barrier for physical travel or communication, they hoped to exploit entanglement to achieve faster-than-light transmission of information. Though the results were promising, the fundamental nature of quantum mechanics remained elusive. Faced with the mysteries of black holes, they turned to the idea of holography, a theory suggesting that all the information within a region of space could be encoded on its boundary. This concept, though abstract, offered a tantalizing possibility that the secrets hidden within black holes might be recoverable, encoded in the subtle patterns of their event horizons. The civilization built vast arrays of detectors, hoping to decode these patterns and peer into the heart of the black hole's mystery. Yet, as they pursued these frontiers, they began to sense that some questions might never have answers. The universe, for all its grandeur, seemed designed to withhold its deepest truths. Beyond the observable cosmos, beyond the event horizons of black holes, and beyond the uncertainties of quantum mechanics, lay a realm of permanent unknowability. It was not just a matter of insufficient technology or understanding. It was a reflection of the inherent structure of reality. The realization that the universe imposed fundamental limits did not deter them. Instead, it inspired a new phase of their journey. If they could not uncover all the secrets of the cosmos, they would strive to understand why those limits existed. This quest brought them to the brink of their next great mystery, the multiverse. If their universe was just one of many, perhaps the answers to their questions lay not within, but beyond, the ultimate challenge and the subject of their next pursuit. The multiverse conundrum. The civilization's relentless pursuit of knowledge brought them to a breathtaking yet disorienting revelation. Their universe, vast and intricate as it was, might be just one of infinitely many. The concept of the multiverse, born from theoretical physics and mathematical models, suggested that what they had long considered the entirety of existence was merely a bubble in a sea of countless others. Each of these universes could have its own set of physical laws, dimensions, and possibilities, forming an infinite landscape that defied comprehension. At first, the idea of the multiverse seemed like an expansion of their cosmic horizon, a new frontier promising endless discoveries. If their universe held wonders like galaxies, black holes, and intelligent life, what marvels might the multiverse contain? The possibilities seemed boundless, universes with dimensions beyond imagining, where time flowed in reverse or not at all, universes where the constants of physics allowed for forms of life and matter utterly alien to their understanding. But as they began to grapple with the implications of infinity, the exhilaration gave way to profound challenges. The multiverse was not just infinite in scope, but infinite in every conceivable way. For every universe like theirs, there were infinite others where the laws of physics rendered stars impossible, or where life never emerged. For every intelligent civilization, there were infinite empty universes, vast voids of potential never realized. The sheer scale of the multiverse introduced a fundamental problem: measurement. In their universe, they could explore, observe, and calculate probabilities. But in an infinite multiverse, these concepts broke down. If there were an infinite number of universes with intelligent life, how could they measure the rarity or commonality of their own existence? Any finite data they gathered from their universe, or even from neighboring ones, was rendered insignificant in the face of infinity. Every percentage they calculated, every ratio they derived, collapsed into irrelevance. This issue, known as the measure problem, struck at the core of their quest for knowledge. They sought to understand their place in existence, but the multiverse offered no definitive answers. Were they unique, a rare phenomenon in an otherwise barren multiverse? Or were they just one of countless civilizations scattered across infinite realities? The multiverse held every possibility, but it also obscured every certainty. Their attempts to explore the multiverse were fraught with difficulties. They had developed theoretical models suggesting ways to access other universes, using quantum tunneling or manipulating the boundaries of space-time. These efforts, however, were limited by the constraints of their own physics. The gateways they opened were unstable, and the glimpses they caught of other realities were fleeting and incomplete. Each experiment raised more questions than it answered, deepening the mystery of the multiverse rather than resolving it. Even if they could traverse the multiverse, they faced a paradox. No matter how many universes they explored, there would always be infinitely more beyond their reach. The multiverse, infinite in its nature, presented a boundary they could never cross. Every discovery they made, every insight they gained, was dwarfed by the infinite expanse of what remained unknown. Their greatest achievements seemed small against the backdrop of endless possibility. Philosophically, the multiverse forced them to confront profound questions about meaning and purpose. If every possible version of themselves existed somewhere in the multiverse, what did their actions mean? Were they merely one iteration among countless others, their struggles and triumphs mirrored and contradicted across infinite realities? Or was there something unique about their particular universe, something that set it apart in a way they could never fully understand? Despite these challenges, they pressed on, driven by the same curiosity that had propelled them to the stars. The multiverse, for all its enigmas, was a frontier unlike any other. They sought to decode its rules, to understand the mechanisms by which universes emerged and evolved. They hoped that within the multiverse's infinite variety, they might find patterns or structures that could offer some measure of comprehension. Their work on the multiverse brought them to the edge of a profound realization. If their universe was not unique, then perhaps the answers they sought were not to be found within it. The multiverse was not just a collection of universes. It was a challenge to their very understanding of existence. The boundaries they had encountered in their universe, spatial horizons, quantum limits, entropy, might themselves be mere reflections of deeper multiversal truths. As they stood on the precipice of this understanding, the civilization faced its greatest question yet. If the multiverse truly represented the infinite, was it even possible to know anything meaningful about it? And if knowledge of the multiverse was forever out of reach, what did that mean for their quest for understanding? These questions, profound and unsettling, prepared them for the next step in their journey. If their own biology and technology had once limited them, and now even the multiverse posed insurmountable challenges, they would need to go beyond their current forms of existence. The next phase of their evolution would not merely involve better tools or faster ships, but a transformation of consciousness itself, a leap into a state of being that might finally allow them to comprehend the incomprehensible. The final horizon, infinity. As the civilization evolved into forms of consciousness that transcended biology, even their most advanced minds were drawn toward a singular, daunting concept: infinity. Infinity was no longer just a mathematical abstraction or a philosophical curiosity. It had become the ultimate horizon of their understanding, a boundary that seemed to defy comprehension itself. To grasp it, they would have to confront the very nature of existence, knowledge, and meaning. Infinity pervaded every aspect of their exploration. In the multiverse, it presented an unending landscape of possibilities, where every potential reality existed somewhere. In the quantum world, it manifested as the endless complexity of particle interactions, the infinite dimensions of Hilbert space, and the ceaseless oscillations of quantum fields. On the cosmic scale, infinity revealed itself in the ever-expanding universe, where galaxies receded faster than light, and the observable cosmos became a shrinking island in an immeasurable sea. Their attempts to quantify infinity only deepened its mystery. They had long mastered the mathematics of infinities, from the work of their ancient predecessors to the insights of modern computational models. They understood that not all infinities were equal. Some were larger or more complex than others. Yet, when applied to the multiverse or the quantum realm, these distinctions often collapsed into paradoxes. How could they weigh their place in an infinite multiverse when every possibility existed in uncountable repetitions? How could they calculate probabilities when infinity rendered every calculation both trivial and insurmountable? As they explored further, they began to see infinity not as a barrier to knowledge, but as an intrinsic property of existence. It was not something to be conquered or fully understood, but something to be engaged with, an eternal question that defied resolution. This realization reshaped their quest, turning it inward. If the infinite could not be fully grasped, could it still be experienced? Could they find meaning in exploring an endless reality, even if they could never reach its edges? To approach these questions, they pushed their understanding of consciousness to new heights. They developed forms of awareness that could operate within the framework of infinity, perceiving not discrete entities, but the relationships and patterns that emerged across infinite scales. These minds could process not just individual truths, but entire systems of truths, seeing the infinite as a coherent whole rather than an overwhelming chaos. Yet, even these enhanced forms of consciousness found themselves humbled by the vastness of their inquiry. For every insight gained, infinity revealed new layers of complexity, new dimensions to explore. This pursuit led to a profound philosophical shift. They began to ask whether the act of understanding was itself the goal. Was their drive to explore the cosmos a reflection of something deeper, a fundamental aspect of consciousness that sought connection with the infinite? If so, their journey was not about reaching an end, but about engaging in an eternal process, a dance with the infinite that could never be completed, but would always hold value. As they contemplated these ideas, they turned their attention to the fabric of the multiverse itself. If each universe was a bubble in an infinite sea, what lay beyond the multiverse? Did infinity itself have a structure, a logic that transcended even the physical laws of individual universes? Could there be a meta-reality, a domain where infinities converged and the boundaries of existence dissolved into something more fundamental? To explore these questions, they embarked on their most ambitious experiment yet. They constructed a vast network of consciousness, spanning galaxies and dimensions, designed to merge their collective understanding into a unified perspective. This network, more than a tool, was an embodiment of their quest, a living representation of their desire to engage with the infinite. It allowed them to think not as individuals, or even as a civilization, but as an entity that could glimpse the multiverse from a perspective beyond time and space. Yet, as they prepared to activate this network, they knew they were approaching a final boundary. Beyond this point lay questions that might never be answered. What was the ultimate nature of reality? Was infinity itself an illusion, a construct of limited minds attempting to grasp the ungraspable? Or was it the ultimate truth, the source from which all existence flowed? These questions set the stage for their greatest challenge, confronting the infinite, not as a concept, but as a lived reality. The final horizon of their journey was not a destination, but a transformation, a leap into the unknown, where the boundaries of knowledge, existence, and meaning would dissolve into the infinite expanse. The stage was now set for the ultimate exploration, one that would transcend everything they had ever known. The limits of knowledge. The civilization had reached the threshold of the infinite, poised at the brink of understanding all that could be known, and yet humbled by the vastness of what lay beyond. Their journey had spanned eons, from their first cautious steps into the unknown to their transformation into entities capable of perceiving reality across infinite scales. They had conquered the barriers of biology, mastered the energy of galaxies, explored the depths of quantum mechanics, and ventured into the multiverse. Yet, despite all their achievements, they found themselves grappling with a profound realization. There are limits to knowledge, and these limits are not failures, but intrinsic features of existence. Their confrontation with infinity revealed that knowledge itself might be a process without an end. Each question answered opened new realms of inquiry. Each mystery unraveled revealed deeper layers of complexity. The multiverse, quantum mechanics, and the cosmic scale had taught them that some aspects of reality could never be fully grasped. Whether due to the fundamental laws of physics, the constraints of logic, or the sheer immensity of the infinite, there would always be horizons they could not cross. Yet these limits did not diminish their achievements. Instead, they gave their journey meaning. The civilization came to see the pursuit of knowledge not as a quest for ultimate answers, but as an expression of their existence, a celebration of curiosity, creativity, and the drive to explore. The very act of seeking, of striving to understand, was a form of connection to the universe, a way of participating in its unfolding story. As they stood on the precipice of infinity, they reflected on the journey that had brought them there. Their first questions, born from the simple act of looking at the stars, had grown into a civilization-wide endeavor that spanned galaxies and dimensions. They had built tools to extend their senses, created minds that transcended biology, and explored realms of reality that their ancestors could never have imagined. Each step had brought them closer to the universe, not as an object to be understood, but as a partner in a cosmic dialogue. The civilization realized that meaning was not something to be found at the end of their journey, hidden in the final answers to their questions. It was something they had created along the way. In their exploration, in their relentless curiosity, in their willingness to face the unknown, they had given their existence a purpose that transcended any single discovery. And so, they turned their gaze back toward the infinite, not with despair, but with hope. They knew that their journey was not over, that there would always be new horizons to explore, new mysteries to ponder, and new ways to connect with the universe. They embraced the idea that their role was not to conquer the infinite, but to participate in it, to weave their story into the fabric of existence, and to be part of the endless dance of understanding and being. The limits of knowledge were not walls to be broken, but horizons to be approached, always expanding, always inviting. And within those limits, the civilization found a profound truth. The search for meaning, for understanding, for connection, was itself the greatest journey of all. In the end, they realized that the infinite was not something to be solved or overcome. It was a mirror reflecting their own nature, a boundless source of inspiration that would guide them for eternity. And so, they continued, their journey stretching forward into the infinite, knowing that the questions would never end. And that was precisely why they mattered.